of postings lists where it turns out that some other order ends up um, taking up the least amount of time. But it should work most of the times. So, but it's just that it doesn't guarantee that uh, the processing time will be minimized if we follow this route. Now, what do we do if our query is more general? So, for example, let's take this query, which is the AND of two OR terms, madding or crowd, and ignoble or strife. So how do we process this kind of a query where we also have an OR term? Well, just as for the AND heuristic, we said that the length of the postings lists, the estimate of the answer, if we do Brutus and Caesar, we saw that the length of the answer is going to be less than or equal to the smaller of these two postings lists. Now, when we have an OR term, the length of the answer in this particular case is going to be the length of this list plus the length of this list minus the length of the elements minus the number of elements that are common to both these lists. So this is the familiar set union formula where the size of the set A union B is equal to the size of A plus the size of B minus the size of A intersection B. So one heuristic that we could use to estimate the size of an OR term is to sum the lengths of the two lists which are being ORed. So we can estimate the size of each OR by the sum of its frequency, and this is obviously a conservative estimate because in reality this intersection is going to be finite and the actual length is going to be smaller than the sum of the lengths. But because we don't know what this intersection is unless we actually calculate it, if we are just given the length of A and the length of B as given by the document frequency field, the best possible estimate that we can come up with for the OR result is the sum of the lengths of the two postings lists. So when we have an OR term and we are taking the AND of several of these OR terms, how do we know which, so this or this, something or something ANDed with something else or something else ANDed with something else or something else? How can we, how do we decide which OR operation to carry out first? Again, we can use the document frequencies of the terms, these 6 terms. We can estimate the size of each of these OR terms by summing the lengths of the postings lists for the 2 terms involved in the OR operation. And whichever is the smaller pair of lengths for these 3, we are going to AND that particular pair. So if this length and this length both end up being smaller than this length, that is, this ends up being the largest value when we estimate the size of the OR term, we'll parenthesize in this way, calculate this result first, which we will then AND with this particular result. So here is an exercise. Can you recommend a query processing order for this particular query? Tangerine or trees, ANDed with marmalade or skies, ANDed with kaleidoscope or eyes. And these are the document frequencies of each of the 6 terms. So eyes and kaleidoscope are grouped together because we are taking the OR of that. Marmalade and skies have been grouped together in this diagram because those 2 are together in the OR operation, and tangerine or trees. So how do you decide which pair of terms to take the AND operation of? Anybody? Also, whoever tries to answer, could you also announce your name, just so that uh, I know who you are, because at this distance I can't see your faces properly. So if you can tell your name, maybe we'll be able to have a little bit more personal interaction that way.
Hello, sir. My name is Aditya.
Yeah.
I think it should be eyes and kaleidoscope first because that's approximately 29,000. Followed by tangerine and trees because that's something like 36,000, and the last one which is approximately 38,000. So
Yeah.
that
Yeah, that's right. So it's actually one order of magnitude more. So this is 200, and I mean this is about 290,000, not 29,000. There are 6 terms over here, but you're right. Basically, if the sum of these two is the smallest, the sum of these two is the next smallest, and the sum of these two is the largest among these three pairs. So because this is the smallest and this is the second smallest, we are going to do eyes or kaleidoscope ANDed with tangerine or trees. Okay, so I've parenthesized these two terms over here. So we're going to take this AND operation first, and then we are going to do this particular AND operation. Is that clear to everyone? Now how about a not?
hello.
Yeah.
Hello, sir. So what's the reason for doing it in this order exactly? Like, what's the real benefit?
So the real benefit is the same that we saw last time, which is we want to minimize, preferably as far as possible, we want to minimize the size of the intermediate results, because the intermediate results are going to be used for further operations. And if the length of the intermediate results is small, then recall that all these operations, these Boolean operations take time proportional to the lengths, right? At least the walkthrough of the pointers takes time proportional to the lengths of the two lists. So if the length of any of the lists can be reduced, then we end up minimizing the total amount of time to process this query. So that's the motivation for.
Hello, sir.
I mean, this again, this doesn't guarantee that this particular method will minimize the processing time. Again, you can construct examples where this won't work. So this is just a heuristic. What were you asking? Sorry, did I interrupt you?
Like, no, sir. Like, I mean, I was saying that the three OR operations, they have to be done in all cases, right? So how does it matter what order we do it first, sir?
Yeah, the three OR operations will need to be done in any case, right? But we are talking about these two AND operations. Ultimately, after taking these three OR operations, you have these two AND operators, just like we had this query. So the difference here is that instead of having single terms over here, each of these three operands is an OR result. Right? So it's a more complicated example where you have an OR result instead of single terms. And so here we just looked at the lengths of the postings list for these single terms directly in the dictionary. Now, because it's an OR result, you'll have to calculate the length of each of these three operands, and you'll have to do that by taking the terms inside the OR bracket and adding up the lengths of the postings list. So you're right. I mean, we are not trying to minimize the work by choosing between these OR operations. We have to do all three OR operations. We don't have any choice on that, but we do have a choice on these two AND operations. Does that answer your question?
Yes, sir.
Okay. Now let's take another. So one of the reasons why we are taking this AND operation is because AND queries are the most common queries on the web, and also in other cases. So somehow or the other, people tend to when they type queries, they tend to think of all the terms as, or at least most of the terms as far as possible, as necessary to be present in the document. So let's look at this AND operation. Friends and Romans and not countrymen. So now instead of an OR result, now you have a NOT result. The third term is a NOT result. So how do we decide which of these two AND operations to do first? We can estimate the size of the NOT result this time pretty exactly by taking the number of documents in the corpus and subtracting from it the size of the postings list for countrymen. So the length of the postings list for not countrymen, this result, intermediate result, will be the total number of documents in the corpus minus the length of the countrymen postings list. And this length is something you know because you have the document frequency of countrymen stored along with it in the dictionary. So this pretty much finishes this section on query optimization. Are there any questions before we move to the next section?
No, sir.
Okay, so last time and also in the first lecture we saw that when we were constructing the term document incidence matrix, we were ignoring the positions of the words in the documents, and we were also ignoring the counts of the terms in the documents. We were ignoring how many times each term is occurring in a document. We are just recording the presence or absence of a term. Now there's something called the Boolean retrieval model, which is what we have looked at so far. The Boolean retrieval model it's the simplest retrieval model, and it turns out that this is not the retrieval model that is used by modern search engines like Google, although there are some similarities. And some of the ideas, the core ideas that we have learned so far, equally apply to the other model, which we will come to later in this course. But what is this Boolean retrieval model? When we talk about Boolean retrieval, we have to look at the scenario as in two ways. Firstly, the query is a Boolean query, right? What that means is the query is constructed using terms which are then connected to one another using AND, OR, and NOT operators. This is not how how most people type queries into Google. Even though if you look at the advanced search of Google, there's an advanced search tab. If you just go to Google, if you do advanced search, Google does provide you the option of using Boolean operators. But actually the kind of queries that modern search engines accept, they are called free text queries. Free text queries means that you just type in whatever sequence of words that comes to your mind intuitively. You're not consciously thinking of Boolean operators connecting those terms. In fact, as a rough estimate, you can say that when a user types in a set of terms in a Google search box, usually they are thinking of all the terms as being preferred if not necessary. So you can think of all those terms as making up an AND query by default. But I mean, strictly speaking, Google doesn't treat it as an AND query. It treats it as a free text query. and we'll see how free text queries are handled by search engines. The reason we are starting from this Boolean retrieval model is because it's the simplest model to teach and to understand the core concepts. So if you learn the core concepts using this Boolean retrieval model, when we take up the more complicated model, which is called the rank retrieval model using free text queries, uh, at least the core ideas will be clear to you so that we can build on them for that more complicated model. So the first thing that you have to remember about the Boolean retrieval model is that it it it, it employs queries. We are employing queries using these Boolean operators. The second thing you have to remember about the Boolean retrieval model is that each document is thought of as a set of terms. Okay, just think of the analogy of putting balls in an urn or in a bag, right? If you a collection of balls in a bag has no ordering to it, right? In the same way, when we create this term document incidence matrix or this inverted index, which we have seen, we are not we don't really keep track of which word appears in what position in the document. We've sort of lost track of the order of words in documents. We are just recording now which term is present in what document. That's it. So each document is viewed as a set of terms, and the query is basically a Boolean expression using query terms connected by and or and not operators. And the semantics of the results is precise. You exactly know why you've got a particular document in the result. It's because the document matched or satisfied the Boolean query. If it satisfies the Boolean query, it's going to be in the result. If it doesn't satisfy the Boolean query, it's not going to be in the result. There is no gradation. You don't say that this document matches this query better than this other document. Either a document matches the query or it doesn't match the query. That's not the way things are in the rank retrieval model, which employs free text queries. There you have the notion of a distance between a query and a document, and the documents that are returned at the top are the ones that are closer to the query in some way that we'll come to later on. But here there's no notion of ranking. Basically, you either a document matches the query or it doesn't match the query. Now, is there an example of a search that you may be using on a daily basis which employs the Boolean retrieval model? Can you think of an example where you use an information retrieval system that employs this model?
So,
Some other
railway reservations or something?
railway reservations. Well, that's possible. That's possible. I don't know. I mean, I don't use the system that you're talking about. So that's quite possible. There's an even more common system. How many of you have? How many of you use search on Gmail or Yahoo Mail or whatever mail address you use? Have you ever used the search feature in your? Yeah. So email search is a good example of the use of the Boolean retrieval model. So basically, if you search your email, the results that you get will not be ranked according to relevance as you get when you do a web search. They'll be ranked in decreasing order of, basically they'll be ranked in chronological order from most recent first to less recent. And depending on what other fields you explicitly specify in a mail, sometimes you can sort them by sender and those other things, but usually they are sorted by date by default. And if you open your the sequence of results that you get, you'll see that It's based on the appearance of those terms in your emails. It's not based on um, it's not based on this rank retrieval model. So email search is a popular example of a Boolean retrieval search. And in fact, the Boolean retrieval model was the primary way IR systems were built for 3 decades until the web came along. And it's still used by many professional searchers like lawyers, librarians, and so on. So digital libraries or library catalogs are another example where you can often find the Boolean retrieval model today. One thing I want to point out is that information retrieval systems come at different scales of operation. So when we think of information retrieval systems, of course, web search comes to our mind the most immediately. But there are also IR systems that are built on smaller scales. Web search is sort of the largest scale IR system that there is. But if you look at desktop search on the other extreme, so I hope you can see my screen here. So I have this Windows 7 machine, and let's say that in this search box I start typing the word ancient. Okay, you can see that as I'm typing this word, I'm immediately getting a set of results over here. And for example, this document is returned because it has ancient in the title. And I don't know why this document is returned. Let me just see. Okay, so this is a video lecture on ancient Greece. So you can see that ancient appears in the title. So that's why this was returned. So this is an example of desktop search. The earlier versions of Windows, I'm not sure about Windows XP, but definitely I think Windows Vista onwards, the operating system itself provides you a system to search files. And again, it's done by building an inverted index and taking your query and then searching that index. Whereas if you look at older versions of the operating systems, if you search for particular files, it's going to take a long time, just trying to search whatever files there are on your system, and then the results will gradually appear one by one as you wait. Whereas here, the operating system would have already built this index, and it's just looking up the postings list for this particular term and immediately returning the documents in which this word appears. So this is the smallest scale IR system that you can think of, which is desktop search. The largest at the largest scale you have web search, but on an intermediate scale you have what is called as enterprise search, where you have a set of documents that are internal to a company and maybe even private to that company's intranet, and you provide a search system which searches documents within that corporate intranet. So you can build an inverted index for a corporation's own internal documents. Alternately, there's something called domain-specific search, sometimes also called vertical search. A domain-specific search or vertical search, which provides search over documents within a particular subject area. Like, for example, there are some search engines which particularly deal with just health queries and health-related documents. So one of the subsidiaries at Cosmix of Cosmix called righthealth.com is such a website which provides you search over health-related documents. Likewise, there are popular databases like Medline and PubMed, where you can search for articles on biology or medicine related papers. So you can type in queries, and the documents that you get will be basically technical papers containing those terms. So that's enterprise search, and I'm going to give you one example of enterprise search in a little bit more detail, And this is the example of Westlaw, which is a company. It's a legal search company. So basically they have this huge corpus of legal documents. So every point from the law, for example, the law of the country, or all kinds of laws will be written down, and legal cases that have been going on in court and so on. They'll have documents pertaining to all that. And what people do is, especially lawyers, they subscribe to Westlaw, and by subscribing to Westlaw, you gain access to those documents. So you can enter Boolean queries, and Westlaw will retrieve documents based on what your Boolean queries are. So they have about 500,000 subscribers even today, who perform millions of searches a day over tens of terabytes of text data. So this company was started in 1975, and even today most people tend to use Boolean search on Westlaw. So they tend to use Boolean queries which they connect using various Boolean operators, even though Westlaw has added ranked retrieval since 1992. So why do you think that lawyers would continue to still use Boolean queries even though they've been provided the option of using ranked retrieval? I mean, ranked retrieval is something that people use all the time on Google and all. So why would anybody still prefer to use Boolean queries?
Like lawyers, they may have a a general idea of what they're looking for already. So so they just want to narrow it down. But they're probably, I'm thinking like in a web search scenario, most of the time you don't know what's going to come up. So I think that could be. I think that could be a reason.
Okay. So you're saying that lawyers have a precise idea of what they're looking for.
At least a general idea, like maybe some case was there or something like that, and they want a precedent, so something like that.
Yeah. The other thing is that as we just saw, Boolean retrieval systems have a very precise semantics. When you get a result, you precisely know why you got that result, because it matched your query. There's no fuzziness in that. So as long as your query is precise enough, you can be guaranteed that whatever results you're getting are matching, or are relevant to the query. And particularly if you look at professions like lawyers, they may often be interested, they may also be interested in in the precise language that is being used in the document, right? So they can be very precise in how they build up their queries, and they would be interested in every single document, so they don't want to miss any document that could be relevant to them, right? So here's an example of the kinds of things that a lawyer could search for on Westlaw. So let's say there's a lawyer who wants information on the legal theories that are involved in preventing the disclosure of trade secrets by employees formerly employed by a competing company. Okay, so you're working at a company and then you go and work for a rival company. So what laws are there to prevent you from disclosing information that you had at your previous company to this new rival company that you're working for? So if you want information on that, this is the kind of query that you would submit to Westlaw. You would say, give me all documents which contain the phrase trade secrets. So this double quotes it signifies a phrase query. A phrase query is a query where you can have more than one term, and the exact phrase must appear. in the document. So it won't do to have trade and secret both appear, but appearing in different paragraphs, for example, or secret appearing before trade. That's not a good match. Trade secret must appear as it is as a phrase in the same sentence. So this slash s is a formal notation saying I want the phrase documents which contain this phrase trade secret in the same sentence as a word starting with disclos, right? And this wildcard, this exclamation mark is basically like a wildcard character. It's saying any word that starts with disclose, and this is to indicate that whether this is to handle variants of this word. So disclosure, disclosed, disclosing, these are all different forms of the same verb, and you can get all variants of that word. You can capture all the variants of that word by having this uh, a wildcard query. In the same sentence as the word prevent, in the same sentence as the word employee. Again, as a word starting with employe. So look at the precision of this query and also the length of this query. So think of a sentence which satisfies this query. What kind of sentence would that be? It would have the phrase trade secret, it would have a word starting with disclose, it would have prevent, it would have a word starting with employee. So it's going to most likely match this information need. So professional searchers know how to translate their information need into a precise query. And in a Boolean retrieval model, in a Boolean retrieval system, they feel that they have power and transparency over what they are getting in the result. Right? Because they are deciding what query to submit, and they know that every document that they are getting in response is going to satisfy this query. So here's another information need. What are the requirements for disabled people to be able to access a workplace? So again, the query could be something like, I would like all documents having a word starting with disab in the same paragraph as a word starting with access, in the same sentence as one of these. So this is another departure from Google search, where spaces in Google search usually can be interpreted as the AND operator, although as I said it's not precisely AND, but you can think of spaces as by default as defaulting to AND, but here spaces default to OR. So you want in this sentence either the word worksite or the word workplace, or you want employment within 3 words, within 3 places of the word place. So this /3, so you're seeing these operators, right? /3, /s, /p. These are called proximity operators. They indicate that I want this word in the same paragraph as this word. I want this word in the same sentence as this word. I want this word within 3 words of this other word. And likewise, you can think of this. Here's a third example. I'd like all queries where you have a word starting with host in the same paragraph as a word starting with responsive, or a word starting with liab in the same paragraph as a word starting with intoxicate, or a word starting with drunk in the same paragraph as guest. So space is disjunction, not conjunction, and this was actually the default before the modern search engines came along. And they have long, precise query. In fact, the average length of a query on Westlaw is 10 words. Do you know what the average length of a query on modern search engines is? Take a guess.
2 to 3.
That's right. So it's 2.4. So you can see that there are, on Westlaw, these professional searchers, and professional searchers are really professional. I mean, they are trained to translate information needs into queries. So you could be a lawyer who doesn't know how to search, so you can hire one of Westlaw's uh, uh, searchers to translate your information need into a precise query. On the other hand, you can't train people who use Google or Bing or any of the modern search engines because there's such a staggering variety of users all across the world. It's just impossible to train everyone. And that's one of the reasons why you find these Boolean operators only in the advanced search feature of Google, because most people don't, you'll never be able to train them to use Boolean queries. Maybe if you are in computer science or a related field, you might be used to thinking of queries as combinations of Boolean operators, but others can't be trained like that. They're going to type what they type, what they're going to type.
So,
Yeah.
are there proximity operators even in Google?
No, there are no proximity operators
I've
in
used
Google,
only
but there
Boolean
are.
and stuffs, but not the proximity.
Sorry.
I've used the and or and double quotes, but not the proximity. So
Yeah, proximity operators are not there, but there is a way to handle proximity
okay.
without having these operators, and we'll see that either later in this lecture or in the next lecture. One of the ways, let me just tell you very briefly how we could handle proximity operators without actually having uh, an operator per se. One of the ways you can do that is by defining a document not as a single file, but as a single paragraph. Right. So, for example, let's say I want to implement this proximity operator /p. One way to do that is not to introduce an explicit operator, but to say that every document that I'm going to look at is going to be a single paragraph. Right. So if a file has multiple paragraphs, I could treat every paragraph in it as a separate document with its own doc ID. So that way, when I get uh, when I have an AND query, I could and I get a particular document as a result, I know that it must have, those words must have been appearing in the same paragraph.
And how
We'll,
about wildcard entries
yeah,
in
wildcard
Google?
entries. Um, Wildcard entries. Well, let's try it out. Okay, let me just type my first four names and then star. Well, it doesn't interpret it as a
Yeah.
wildcard query. So here's the thing, right? Wildcard queries are again queries that probably only professional searchers would use,
Yeah.
right? So it won't be the priority of a modern search engine to handle wildcard queries because most users are not going to use it anyway. Even Boolean search is available only if you click this advanced search tabs. You find, then they ask, you want web pages that have all these words or this exact wording, or you have this or operator over here. Okay, so this is the and, this is the or, and you want to exclude these words. So these are, this is like the not operator. So, and of course you can specify other constraints. You want only English documents and so on. But, this is not going to be used by most people. In fact, um, what was the statistics? I think it's definitely less than 10% of people who. So phrase queries are something that people tend to use more often, right? You can use. You probably used phrase queries, right? Where you use double quotes, and the documents that you get will be documents which have this exact phrase. So phrase queries, I think 10% of searchers on modern search engines, something around 10% have used phrase queries. But Boolean search, I mean, it's going to be much less, maybe 1%, less than 1%, something like that. See if you can find out what the exact statistics are for that. But the point is that because most users won't be using wildcard queries, it won't be the priority of a search engine to handle them. We will learn how to handle wildcard queries in a couple of lectures. So you'll learn how to do that. In fact, that should also help you understand why search engines would prefer not to have wildcard queries available too freely, because it's a pretty expensive operation to process wildcard queries. And you'll see that in a few lectures from now. Any other questions?
No, sir.
Okay, so now you know how to build a simple search engine. Right? You can build a Boolean search engine on your own. Does everyone feel that? I mean, I'm not going to ask you to build one, but do you think that in principle you could now go and straight away say build a search engine on say Shakespeare's corpus, something like that?
Theoretically, yes.
Okay. Well, if you know, if I was an on-site teacher, I would probably give you a project or something like that to actually build one. But I mean, if this is the best way to learn, in case you want to go ahead and do something
Just
like
give
that.
us an idea so that we can try it.
I think whatever we've discussed so far should be enough, right? You
No, not the theory part, the practical part.
The practical part would be, again, it would be similar to, I mean, we have discussed the practical part only, right? I don't see any separation here between theory and
No, suppose
most
I
of,
have
yeah.
10 text files and how am I going to create that index? See, theoretically, I told that I'll get these many words and those many frequencies, I have it. Okay, done. But how am I going to initially search and put it into a index or something like that?
You saw that pipeline, right? We had this pipeline where you're going to parse each document.
Yeah.
You're going to parse each document. You're going to split it into tokens. Again, you can use some very, very simple tokenization schemes. We're going to look at tokenization in more detail either later today or and also in the next lecture. Then you can use linguistic pre-processing of some kind. I mean, even if you don't use this, it's okay as long as you use some primitive a normalization scheme where you map different variants of a word onto the same word. And then you do this sort operation, right? So this is sort based indexing where you take this stream of normalized tokens, you sort it, and then you create this dictionary data structure, which could be implemented either as a sorted array or as a B tree or a hash table. And then these postings lists, and if you're working with a small corpus, the postings lists are going to fit into memory. So you can use variable length arrays or linked lists based, depending on what exactly what kind of system you exactly want to build, what the use cases will be, and so on.
Okay, we'll just try it, sir, this weekend.
Yeah, sure. Although, I should say that in reality, there are open source tools available. You don't actually build a search engine from scratch. You actually use this open source software which already has a built-in facility for building a search engine. For example, if you've looked at Wikipedia, so Wikipedia search is built using an open source engine called Lucene. So whatever you type here, this is going to be processed by their own search engine, which is built on the Lucene platform, and that's what you get in the result. Likewise, if you look at Amazon or Walmart, those are also enterprise level search engines. I mean, they also provide enterprise level search. So, pretty much everybody is using. I mean, most of the online websites use search.
So the platform you named for the Wikipedia, what we didn't get that.
It's called Lucene.
Oh, okay.
I'll talk about it in slightly more detail later on. So right now, I mean, I just mentioned the name. You can search for it, but um mostly, there's no point in reinventing the wheel if there are ready-made open source
Yeah, yeah.
softwares available
That's
for
correct.
you.
That's correct.
So, okay, so let's look at some of the things which our primitive search engine cannot handle. We don't have spelling correction, right? We have no way to correct for spelling mistakes in the engine that we have built so far. Even though I told you that Westlaw uses Boolean queries, you can see that getting some disturbance. Uh,
So your voice is breaking.
yeah, I'm getting some disturbance also. Now is it okay?
Yeah, it's okay.
Okay, okay. So you can see that even though we've talked about Boolean retrieval so far, this particular model where queries are not purely Boolean expressions, you also have these proximity operators, wildcard queries, phrase queries. These are not, I mean, we haven't seen how to implement these kind of queries, right? We haven't seen how to process these kind of queries. So what Westlaw provides you is actually something called the extended Boolean retrieval model, where you also have these additional proximity, phrase, and wildcard operators. And we're going to see how to handle these extensions maybe in the next lecture or the lecture after that. So this is something we need to learn. Okay, we need to learn how to handle phrase search, where the word uh, university must appear after Stanford, immediately after Stanford. So you can guess that we'll need to keep track of positions of words within documents in order to handle phrase search and also proximity search. Right? If you want gates within the same sentence as Microsoft, you need to keep track of positions of words within documents also, and that is something we haven't kept track of in this simple search engine, which is why we can't we can't answer such queries. So we'll see how to augment the inverted index we've built to handle these two queries. The other thing we haven't given any attention to is ranking. I did mention that Westlaw returns documents in sorted by date, most recent first, and many of the simple search engines that you see, in the library catalogs, email search, and so on, they do this kind of primitive ranking, you can say, and that can be added even to our simple search engine, right? You can look at the document creation time or something like that, and then make sure that when you are returning the list of documents in the result to the user, you sort it before returning it. So you can do some kind of post processing on the results that are returned and sort them by in chronological order, and that you can implement a very simple ranking that way. But when we talk about ranking, we are mainly talking about relevance. We are talking about more relevant documents appearing before less relevant documents. And how do we calculate relevance? How do we determine that this particular document is more relevant to a query than that particular document? That's something we haven't discussed, and we're going to look at that in detail later on. Uh, the other thing is, let's imagine a query like, let's say Peacock, right? Suppose there is a document which mentions the word Peacock once, and there's another document which mentions the word Peacock 20 times. You can argue intuitively that this document is probably going to be more relevant to me than this particular document, because if the word peacock is appearing 20 times, the likelihood is higher that the entity peacock is one of the main topics, or if not the main topic of this document. Whereas, if somebody is mentioning peacock as an aside in some document, then that may not be so relevant to my query. So Again, we haven't kept track of how many times a particular word appears in a document, right? We just discarded that information. We are just keeping track of presence or absence so far. So if we may want at some stage to give more weight to how many times terms appear in documents. Okay, and consider those documents which have a higher number of term instances appearing to be more relevant than another document where the term appears only once. So I would like to introduce this term, this terminology here called term frequency, which is the number of times a particular term appears in a particular document. Okay, term frequency of a term T in a document D is the number of times the term appears in that document. Note that unlike the document frequency where you only need to specify the term, right? Because this is the length of the postings list for T. This is a function of two parameters, the term frequency. You need to specify not just the term but also the document, and it's going to give you how many times that term appeared in that document. Or this is, the number of documents containing T. Now this is going to be, both these frequencies are going to be pretty important later on to us. So I don't want to, suddenly introduce this term when we're going to use it and then start using it in a complicated way. So I'm just giving you the definition in advance so that you have some time to absorb and remember it, so that we can move to more complicated things using these formulas later. So here's a summary of how the user interacts with an information retrieval system. So you have an information need. That information need is translated into a query, and if you are a professional searcher, you would probably know how to do this pretty accurately. But in general, most people who use modern search engines may actually end up misformulating their information need when they express it in a query, as a query. You may have noticed this with your relatives or people who are not computer savvy. When you ask them to type something, they may type something that you would think is relatively naive. It's not going to return what the information that they're looking for. So the more you're familiar with the web, the more accurately you would know to translate this information need into this query. For example, let's say somebody's information need is to trap mice alive. Okay, they want to find out how to trap mice alive, and they may just search for the phrase mousetrap. Now, it's possible that if when they actually search for mousetrap, they may get something else, right? For example, this is the top result here is a brain game called Mousetrap. It's a board game, as you can see on Wikipedia, and they may get some other result. This is a murder mystery play by Agatha Christie, Mousetrap. So you can see that these results are not really relevant to their information need, which is to trap mice alive. So there can be some misformulation here. But anyway, this query would then be submitted to a search engine, which would have built an index on a particular corpus, and it would consult that index to answer the query. So it would return a list of results, and if the results satisfy the user's information need, well and good. Otherwise, the user would refine the query and submit it again to the search engine. So in Westlaw, for example, lawyers may start using a short query, and then in the results they may find that they are getting too many results, tens of thousands of documents. So they may try to filter out some of the less relevant documents by extending the query, saying, okay, I don't just want these 4 possible words in this sentence. Let me add another let me add another /s followed by some other term to filter down, to filter out these results. So these queries are incrementally developed in Westlaw. You start with a relatively short query. If you find that there are too many results for you to wade through, you extend your query by adding more proximity operators and so on to narrow down, or to filter out, or to filter the list of documents to a smaller, more manageable number. And a similar thing can be done on a modern search engine, where you can refine your query if you don't get what you're looking for. So of course we can't do anything about this. We can't do anything about training the user to translate his information need into the query better, but we can look at whatever's happening below this query box. We can improve the engine itself. Now, how do we evaluate the performance of an IR system? There are two metrics that are used to evaluate how good the results are. The first metric is called precision, and the second metric is called recall. And again, I'm introducing these terms because if you have friends who are in the IR community, they would be throwing these terms around almost like teenagers throw around the words like and duh and all those kind of words which people tend to throw in every sentence. So like that, if you if you ever work in a company where people are expert in IR, these words are like ABCs to them. So it's something that I'd like to introduce here, because again we'll be using this later on. Precision is the percentage or the fraction of retrieved documents that are relevant to the user's information need. So let's say you type a query into a search engine, and you get 100 documents in the result. Now 70 of them are relevant to your information need. In that case, the precision of the results would be 70%. So among all the retrieved documents, look at what percentage are relevant to your information need. By the way, this relevance is calculated with respect to your information need, right? It's not calculated with respect to the query. Although in our Boolean retrieval example, the two were kind of the same, right? Because either a document matches a query or it doesn't match a query. And if there's any problem, the problem is only with the translation of the information need into the query. But once you specify the query, you exactly know why you've got the answer. But here, in a search engine, that may not be the case. I mean, you often may not exactly understand why you got a particular document in response to a particular query, because the results are not based on a simple text match. They could be based on, you'll see what they're based on. They could be based on certain calculations which end up being, even if somebody types in a query like drug abuse, you may get something like substance abuse or cocaine abuse in a document that is returned in the result, because those phrases are deemed as relevant to your information need. So precision is something that you have to, a user has to decide. So there is some subjectivity here in calculating whether or not a particular document is relevant to you. Recall is the other measure. So let's say you type in a query like peacock, and suppose there are 1 million documents in the corpus which talk about peacocks. But okay, peacock is a simple query. You'll probably get all 1 million of them. But think of a more complicated query. Flights to New Delhi, for example, or flying to New Delhi. Okay, there may be, so you may want to get all documents which talk about how you can book a ticket to New Delhi. And there may be, say, let's say 100 websites which offer you tickets, flight tickets to New Delhi. but let's say only 60 of them are returned to you in the result. Then the recall is 60%. So here's a simple question. How can you have 100% recall? What is the simplest way to have 100% recall? So what do we want in general? We want a higher precision and we want higher recall. Right? You want that all the results that are returned to you should be relevant. You also want that all the relevant documents in the corpus should be returned to you.
Boolean search.
100%.
Boolean search.
Will Boolean search do that? For example, again, we can have a query like substance abuse, and let's say, or you can have a query like diabetes, for example, and there could be a document talking about high blood sugar without really mentioning the word diabetes. So that would be relevant, but it may or may not be retrieved. This is actually a very trivial question, and the answer is a little silly, but if you return every document in the corpus, you will have 100% recall. Because if you are returning every document in the corpus, you are returning every relevant document in the corpus as well, right? So 100% recall is easy to get. You just return every document in your corpus. But what's the problem with that? You'll have very low precision. Because most of the documents that have been given to you are junk. They're not relevant. How can you have 100% precision? So notice that it's very easy to have 100% recall. The problem is that the precision will be low. How can you have 100% precision? Well, let's say you just return one document, okay? Let's say you are very, very conservative in your in how you measure the distance between a query and a document, and or let's say you necessarily do an AND query no matter whatever query you give. So every document that is returned to me will be returned because it contained all the terms that I typed. So that's likely to maximize the precision. In fact, just think of an extreme case like this one where you just return one single document. That way I can get 100% precision, because if I'm returned one result and that result is relevant, then I'll have 100% precision. But the problem is that the recall will be very low, because there would be many other documents in the corpus which were not returned. So you can see that there is some kind of tension in improving precision.
Are they always inversely proportional, sir?
They are not always inversely proportional, but there is some kind of tension. Often if you try to maximize precision, you will end up compromising on your recall. And if you try to maximize recall, if you adopt some techniques to improve recall, they may end up reducing your precision. So the best possible scenario is where you come up with a technique which will improve both precision and recall.
No, for example, when we are using Google, we won't go to more than the third page. So recall, is it very much required to have a greater recall than a greater precision?
Yeah, that's a good question. So lawyers tend to, so again it depends on the users, right? As you said, most people won't look past the first 20 or so results. But if you look at this particular example of Westlaw, recall is very important for lawyers because they don't want to miss any document that could potentially have a bearing on their case, right? So they would want to look up every single result that is returned to them, just so that they don't miss any loophole. Maybe one of the documents could talk about a potential loophole that they would miss. So it all depends on the background of the users, what kind of documents there are in the corpus, what kind of search system you're using. But you're right that recall may not be as important as precision for normal users. So that's why you have to think about precision and recall, what you want to maximize based on what your user base is, who you are serving, and what their requirements are. Any questions?
So the query optimization or the search engine optimization comes into picture here, right?
So query optimization is different from search engine optimization. Search engine optimization, which is actually a technical term, it's called SEO, is how do you optimize your web page so that it appears high in the list of rankings on Google search or some other, any other commercial search engine. Because if you are a company that has an online business, then you want to improve traffic to your website, right? You want more and more people coming to your website and shopping or clicking on ads or whatever. I mean, doing something that will benefit you financially. So for that, you may want to increase traffic to your website. You would want your website to appear close to the top in Google rankings on general queries as far as possible. Right? If you have very, very long, if you have very, very rare queries, they're usually called tail queries, which not many people. So tail queries are the queries which are very rare, which appear very rarely in the query logs. So query logs is basically think of the query logs as the set of all queries that somebody submits to a search engine. All the users across the world. Think of pooling together all their queries into query logs. Now tail queries are queries which appear very rarely. So if somebody can reach your website only by only via these tail queries, then you won't get much traffic, right? You want that just by typing in some common word, people reach your website. So SEO is about how do you optimize your website so that you get a higher traffic as a result of appearing higher in the Google rankings.
Okay.
Query optimization is we'll look at SEO if we get the time later on in the course, because this is again an important part of commercial IR systems. How do you maximize revenue and so on? But
every company would do the same thing, the search engine optimization, right? But how does the Google take which one it has to accept and which one not to accept?
So we'll look at that.
Google?
Yeah, I mean they have, like, for example, PageRank is. So here's one thing one way you could try to spuriously fiddle with how search engines rank you, right? You could fill your page. Let's say you have a website. You could fill your website with just junk, right? You could fill in very popular words which people type in very commonly on a search engine. So think of building a spam page. Right?
Okay.
There are lots of spam pages out there. You can just fill your documents with all kinds of commonly occurring words, but basically having no content as such. So you can construct such pages, and that's what many people try to do, so that they can get ranked higher in the rankings. But of course, Google developed this PageRank algorithm, where the importance that they would give to your page would depend on how many other authoritative pages point to you. I mean, intuitively. So how likely is a random user? How likely is think of the web as a graph, right? So if there are a lot of authoritative web pages pointing to you, it is likely that somebody browsing authoritative web pages will reach your page. So your page will also be deemed as authority in that case. But if nobody else is pointing to you, or if it's your own website where you have these internal cross links, then your pages won't get a high page rank. Your website
Okay.
will not get a high page rank, and so it will be pushed down. So now search engines are pretty sophisticated. They look at whether if you just copy somebody else's page content, for example, they have ways to detect that, and they'll blacklist you or something like that. So that you won't appear high in the rankings.
Okay.
The other thing that people do in order to drive traffic is to have advertisements.
Yeah, Google Ads,
Okay, so if you type,
AdWords.
yeah, so uh, let's say I type a query like headache pill, right? So I'm going to get these ads over here, headache relief. I have this other text link here. So these are all advertisements. So you can also companies can pay Google to advertise their content on particular search keywords, and that's another way to get traffic. But here you're paying for it. In SEO, in search engine optimization, you're appearing higher in the ranks thanks to high quality content on your page. So you're basically getting free traffic that way. But here you have to pay in order to get traffic. So this is called SEM, search engine monetization, where you have to you have to bid on particular keywords, and people typing in that particular keyword in the search box will see your ad. So hopefully we'll come to that later in the course. Any other questions? So we've pretty much finished with chapter 1 here. So if there are no further questions, we'll move to chapter 2. One of the things I want to mention, which I didn't mention over here, is you could do pretty sophisticated post-processing on your search results. I did talk about sorting the documents in chronological order of creation or something like that. But you can do some more sophisticated post-processing. For example, you could cluster your documents into one or more groups. For example, the most popular example of this is a query like Jaguar. The word Jaguar stands for an animal, but it also stands for a car. It also stands for an operating system. So it has different meanings. So if you just type the word Jaguar, some search engines may want to cluster the results that they return into different meanings of the word Jaguar, right? So you would see one set of results for Jaguar the animal, you would see another set of results for Jaguar the car, and so on. So that would be called as clustering, where you detect certain clusters in your sets of results, and you group your documents based on what are the different meanings of that particular term which appear in all those documents. Okay, so given a set of documents, how do you group them into various clusters based on their content? That's the job of clustering, and we're going to see that later in the course. That's one kind of post-processing. The other kind of post-processing is called classification. So you could classify a particular document as a news-related document, or
Hello, sir. I have a small doubt.
yeah.
Sir, before we move on to the next topic, sir, I want to know how can we balance recall and precision?
How can we balance precision and recall? Well, we'll look at some techniques. I mean, one of the simplest ways to do that is to that we're going to look at shortly, is to improve the quality of your tokenizer and linguistic pre-processing. This particular pipeline that we saw. There was that. This one. So if your tokenizer works properly, and if your linguistic module is sophisticated, you can get higher precision and higher recall.
Okay, so there is one
For
small
example,
idea which is coming to my mind.
Yeah.
Okay, that is like if we in each document if we could track number of appearances, so the documents which has least number of appearance could be avoided in order to get good precision and recall. So is that a good idea?
When you say appearances, you mean what exactly?
Sir, as like before we saw the same document having say suppose 20 words like peacocks, and other document having just one. So now if we could collect all the documents which has more appearances of peacock, so that could also be one method where we could get recall.
Where you could, well, so recall is measured based on the total number of results that are returned. Right. So right now, let's just forget ranking for now. Okay, how this, because you know, you also want those more relevant documents to appear at the top. So how do we do that? That's something we'll measure later. But for now, as long as all those documents are appearing somewhere in your search results, you can think of recall as being high. Here's an example, right? Here's an example of, we saw this last time. Let's say you don't normalize friends into friend. Right? Let's say you don't do this. Let's say you don't have this linguistic module over here. So friends, Romans and countrymen would be, would enter your index as friends, Romans and countrymen. Now if I search for, if I have Roman, just the single word Roman in my query, then I won't get documents containing the plural form of this word in the results, because this plural form was entered into the index as it is without being normalized. So I will look up this postings list for Roman and I'll get all documents containing the word Roman, but I won't get documents containing the word Romans because that would have been indexed separately rather than being mapped to this same term. So that would result in low precision. Sorry, it may not result in low precision, but it would result in low recall. Right, because I won't be getting these other documents which contain the word Romans, even though they could be relevant to me. So now you could improve your recall by adding this linguistic module without sacrificing on precision. Is that clear?
Yes, sir.
And throughout, we'll see techniques to that will improve. I mean, it depends on how, what is your base standard from which you want to improve. I mean, if you have a pathetic search engine, you could do very, very simple things and improve both precision and recall that way. But as your performance becomes better and better, it becomes higher, it becomes more difficult to improve both precision and recall without sacrificing one for the other. Okay, so just to summarize, what we have discussed so far is, we have talked about what data mining is, we've talked about what information retrieval is, we have built an IR system from scratch, an inverted index, we've used it to process Boolean queries, we have learned how to optimize those Boolean queries, and we have looked at several examples of applications of Boolean retrieval model. And we have also looked at some of the limitations of the model or the engine that we have built so far. It can't handle phrase queries, proximity queries, and so on. I just want to show you this particular feature. I don't know how many of you explored Google Zeitgeist, but I was talking about query logs and how you can mine the query logs to figure out what queries you're getting. Now you can aggregate the the queries that you're getting from different regions in the world and figure out interesting patterns. You can figure out, what a particular, what is the current fashion in a particular culture, or what are most people thinking
So,
about when they search online.
so can you hear
So,
me?
yeah,
Sir, actually, there's a doubt regarding the previous Boolean search.
right.
Okay, you said when you type something it takes it has a slash p or like a slash s.
Yeah.
How actually it takes that how
When you say how exactly it takes, that means what exactly is the semantics of this query? Or how is this query processed?
Sir, actually, whenever we give an sentence for the search, how does the query engine take whether it is a slash s or slash p? I mean, whether it's in the same paragraph or whether it has to take in a sentence, because we don't specify whether it is it has to be present. It takes only the keywords, right?
Yeah, so what I said there was that even though the implementation of a search engine that we have seen so far handles only Boolean queries, the Westlaw search engine, the Westlaw retrieval system is an example of an extended Boolean retrieval model. So this word extended is indicating that it's doing something more than what we can handle using the engine that we have seen so far. Right? It's handling proximity queries, it's handling wildcard queries, it's handling phrase queries. The engine that we have seen so far cannot answer such queries. So your question is, how can a search engine handle such queries? And that's something which we are going to discuss maybe in the next lecture. We'll see how to augment the inverted index that we have built so far to capture positional information as well. You will need to capture the positions of terms and documents in order to handle queries like this. So how exactly we do that, we'll see in the next lecture.
Thank you, sir.
Sure. So I don't want to introduce it suddenly here because I want you to take
Sir, your voice is breaking actually.
Is it clearer now?
Yeah, now it is clear.
Yeah. So if you take some time to understand what we've done so far, then when we make things more complicated, when we add more features to our search engine, those features will be easier to understand for you. That's why I'm having this break. So in fact, I'm following the order in the book. So the second chapter of the book does cover this particular issue of how to handle phrase and proximity queries. But it does so in the second part of that chapter. In the first part, they talk about tokenization, linguistic processing, and allied things in more detail. So that's what we'll look at first, before we look at handling positional information and in order to answer such queries. So I was talking about Google Zeitgeist. Basically, Google can tell you what a particular culture is thinking about at any point of time by mining their query logs. And here, for example, they can tell you a summary of how the world searched in 2010. They can do that for every year. You can look at their archives. They have such information for all the years. But if you look at India, for example, so they have India specific data as well. So they have mined query logs originating from India. And for example, they can, what were the most popular movies that people searched for? Okay, so if appearance in query logs is an indicator, then Kites was the most popular movie in the year 2010. And so on, what were the most popular brands, most popular how-tos, what were, people searching for who are the fastest rising people, who are the most popular, uh, what were the most popular queries. So, for example, so these are all, you can visualize this same summary information in various ways. So, there is this separate field of data visualization where, they teach you how to present your data in such a way that, uh, it's easier to understand. One of the things that ends up being important if you're building an actual search engine is presentation. If you don't know how to present your data properly, then you could have excellent algorithms and you could be returning very relevant results, but you won't be able to get much, you may not be able to make much impact. Carnegie Mellon University, it was called CLUST. CLUST, I think earlier its name was Vivissimo, and then they named it CLUST, and they were very good at clustering results. I talked about this Jaguar query where you could cluster the documents that you're getting in the result into different groups based on what that term means, the different meanings of that term. So they were able to do that very well, but people say that their presentation of the results was not appealing, which is why they didn't do well. So anyway, that's an aside. But I just want to emphasize that visualization or presentation of data shouldn't be taken very lightly. So let's see, fastest rising people. If you look at Salman Khan, for example, you can see that the queries, the queries for Salman Khan were, they fluctuated like this in 2010. So if you mine that data, you can see that in September, for example, there was this peak. Okay, what happened? I don't know what happened in September 2010, but somehow there was a peak there. If you look at Sachin Tendulkar, you can see that the peak for Sachin Tendulkar was different. He peaked over here in February of 2010. Did something happen in February 2010? So these are the kinds of questions that you should be asking. Right? Why do I see this kind of a peak in this particular month? Maybe something was happening which Google is able to capture and mine. In fact, people say that you can often detect the spread of a disease by mining the logs from different regions. So if a particular disease is spreading in a particular geographical area, then there are people doing research on how the frequency with which people search for the word flu varies over time. And if a disease is spreading in a particular region, then you'll see a spike in search terms involving flu. And so that way you can, that's a very indirect way of detecting that a particular epidemic or a particular disease is spreading in an area. So you can play around with this zeitgeist and see what are the different kinds of information that Google mines based on the query logs. Any questions? So let's look at let's move to the next chapter then, and let's go back to that pipeline that we talked about. The overall pipeline for constructing a search engine or constructing an index. The first thing that you need to do is to collect the documents that need to be indexed. Now if it's a search engine, you can go out and crawl documents from the web, or if you have a static corpus, you could just use the corpus, the files that are available to you, and prepare your corpus in that way. But one of the things that we will need to do in practice is to extract this text from these documents. Now you may think that's a very trivial thing, but it's actually not. It's not that every file that you get when you crawl the web will be in text format, right? There are a staggering variety of file formats that can be used. There is a staggering variety of languages in which pages can be written. Even the encoding of characters can be done in various ways. So how do you get text out of PDF documents, Word documents, Excel files, XML or HTML pages, PostScript documents, and so on? That's going to vary based on the file format. So even this particular task, which may appear so easy, is not that easy. You have to worry about the file format. What format is
a dictionary or something which for a reference and get the words comparing to the dictionary?
Are you talking about the language here?
Yeah, the extracting the words from many files.
So when you talk about a file, a file is basically just a sequence of bytes on disk, right? So when we want to extract words from a file, the first thing we have to know, we have to know what the file format is. We have to know what language it's in. So the dictionary thing that you're mentioning applies to the language, but what about the format itself? Right? If you don't know that a particular file is in PDF format, just by reading the bytes, how would you know that? Having a dictionary wouldn't help you, because how will you interpret the sequence of how will you get that sequence of characters in the first place, unless you first decode your PDF file into a character sequence?
Okay, for example, Google doesn't. If we give a search in Google, obviously it will search only for a plain text or a HTML file or a PDF or a Word, or a maximum a PPT or a XLS. That's all. It doesn't search any XML file or anything. Is that what you're talking about, sir?
So I'm not talking about Google in general. I'm just saying that for building any search system, you have to decide first of all what file formats your documents are in the corpus. If your documents are in a variety of file formats, you have to be able to know how to extract a character sequence out of basically that file, and the way you'll do that will depend on the file format. So
okay.
you will need to probably use existing software libraries. Again, this is not something you will do on your own. Information retrieval doesn't deal with this subject of how to extract character sequences from files of different formats, but you'll probably license existing libraries which will do this job for you. If you feed it a PDF document, you should, maybe this software will return to you the text that appears in the PDF document. But basically you'll need to use these, you'll need to use some licensed softwares in order to extract the character sequence from the files. And first of all, you'll need to determine what the format is. Now, one simple way to do that is just to look at the file extension. If you look at whether it's a .pdf file, that would indicate that it's a PDF file. Sometimes, that may not even. There may be issues here also. The file format may not be specified properly, or it may be specified wrongly. These are some practical issues that may come up. And then even when you look at HTML or XML files, which you could probably easily convert into a character sequence, because they would be text documents, you would still need to discard the irrelevant markup, right? The tags and all. Even the ampersand, for example, would be represented I don't know, something like this in XML.
%20 or something like that.
Yeah. So all those things you need to convert into the actual characters. in the content. Language is pretty important because 60% of the World Wide Web is in English, but 40% of it is in other languages. So when you're indexing documents that are in a variety of languages, you have to know what language your document is in, because as we saw last time, tokenization is going to depend on that. Linguistic preprocessing is going to depend on that. So what kind of tokenization and linguistic processing you end up doing will depend on the language, and so you have to be able to figure out what language your document is in. And then what character set is being used by the documents in your corpus. You can have ASCII, you can have Unicode, you can have something like UTF-8, and there are many others. So especially if you're looking at documents written in foreign languages, where you have these diacritical characters and Chinese characters and Arabic, or all kinds of other languages. Clearly, the document is not going to be in ASCII format, so it's going to be in Unicode or UTF-8 or something like that. So sometimes the character set is correlated with the language, but it's something that you have to figure out. Now, the easiest heuristics that you could use is to look at things like the file extension. Sometimes you could look at document metadata. Like for example, this particular desktop search that I did, searching for ancient. Now this is a video file that I got in result, but I'm sure that if I look at the metadata, there would be the word ancient appearing as the title, which is why this search engine was able to retrieve it. It's very hard to read data that's present only in the video. Okay, that's something which is not easy. So document metadata can contain information about the kind of encoding it is, the kind of file format you're using, the kind of language it has, and so on. So these are, and sometimes the first few bytes of a file can contain some kind of signature. PDF files could maybe open, start with a particular byte sequence signifying that it's PDF. So you can rely on heuristics to figure all these out. More sophisticated machine learning techniques can also be used, but in practice, these heuristics do pretty well. Now, what do you propose to do if your corpus contains many different languages? Because what's going to happen is that your index is going to contain terms from different languages. But imagine this document, right? Suppose there is a French email, an email written in French, and an attached file in German. How would you build a search system to deal with such heterogeneity in language? Okay, this is an issue you'll have to think about. So we will assume for now that we know how to extract the character sequence from the documents. Okay, so we're going to use licensed libraries of some kind. We're not going to worry about this problem. We'll just assume that it's solved for us. We have the character sequence for every document. But it's something I'm just pointing out that you will face if you were to practically do this. Now, how do you decide what is a document? One simple way to do it is to look at every file in your corpus and say that it's a document in itself, which is what we did for Shakespeare's plays. Every play of Shakespeare was in a separate file. But think about say a Unix mailbox, right? It's a single file, and all the emails in your inbox could be stored in that single mbox file. So in that case, you would want every email in that single file to be treated as a separate document. Right? What about an email which has attachments like this one? You could have an email with 5 different attachments. Do you want all 5 attachments and the email to be treated as a single document, or would you want every attachment to be treated as a separate document, in which case it will get its own doc ID. Every attached file will get its own doc ID. These are decisions that you will have to make. Sometimes, I don't know if this still happens, but at least in the early days of the web, I remember there used to be PowerPoint presentations which used to get converted into HTML. And, because HTML pages would be easier to load, so people would often convert their PPT into HTML files, and then the whole presentation, if the presentation had 30 slides, there would be 30 HTML pages generated, one for each slide. Now, each HTML page is a separate file, but then you would want to combine all 30 of them and treat it as a single document. Right, so this is the opposite of this Unix mbox example I gave, where you have a single file and you want to treat every email in that file as a separate document. In contrast, you could in the PowerPoint example, you may want to take many different files and treat it as a single document. So I think, are we out of time, or do we still have a few minutes?
So we have 5 minutes.
Okay, so do you want me to continue, or do you want to ask something in these last 5 minutes?
Sir, I'm Salima here. Sir, can you hear me? Mr. Biswajit? Yeah, we'll get the feedback from the students today. And regarding the assignment and the evaluation assignment, I'll mail you so that we can discuss. So is it like the next chapter is being started now, so that only 5 more minutes so that we can start in the next session, I hope.
Okay, so let's see if they have any questions, or unless you have something else to say.
Sir, I hope we'll wind up.
Okay.
So there are no questions right now, so I'll ask them to be more interactive in the next session.
Okay.
Okay, sir. Thank you.
Thank you.